So in the last lecture, we studied about gauge transformation. Okay, it means that you can either you take V or you take any other potential V dash which is related to V as V plus beta, or you take any other potential V double dash. Whatever you do, you get the same electric field E. Similarly, if you take a magnetic potential A, or if you take a magnetic potential A dash which is related to the original magnetic potential as some A plus gradient of some function lambda, or you take any other magnetic potential A triple dash, whatever you do, you get the same magnetic field B. You get the same magnetic field B. This is an amazing thing. It means that it is our choice what A and what V we want to use. On the other hand, I said that Maxwell equations are four equations. They are four equations with six unknown. There are six unknown variables. And then I used the potentials to convert the six Maxwell equations into mainly this equation and this equation. These are the two main equations that contains all the information that is inside the Maxwell equation. So equation number 1 and equation number 2 are the general equation that contains all the information of Maxwell equations. So instead of solving four equations, we can actually solve two equations. And how many unknowns are here? There are four unknowns. As we have discussed earlier, there are four unknowns. Why there are four unknowns? Because V is an unknown and A vector is an unknown. Now A vector has three component, Ax, Ay, Az. So it makes a total of four unknown quantities. Now question is, so what? If I solve these two equations and calculate all the four unknowns, then what happens? Well, what happens is by using the four unknowns you can calculate all the E field and the B field. So once you know the magnetic potential and you know the electrostatic scalar potential, that is by using all the value of four unknowns, that is the four potential, no, there are two potentials and those two potential makes four unknown. So by using these four quantities you can calculate all the six unknowns that were in the Maxwell equations. But then we face one more problem. These two equations itself are very complicated equations. These two equations are itself very complicated equations. So question is, how can we make these two equations simpler? Gauge transformation comes to our rescue. Gauge transformation says, hey look, you can choose any V and any A. Okay. And even if you choose any V and any A and put them in this equation, nothing is going to happen because your E and B field are not going to change. So there were many plans of how can we use gauge transformation to reduce this equation. Coulomb suggested that let us take such a magnetic vector A, I mean such a magnetic vector A whose divergence is 0. So del dot A is 0. So this is called Coulomb's gauge. Coulomb said this, let us do this thing. And then Coulomb said that, hey look, if we do this thing, if we take such a magnetic vector potential whose divergence is 0, then the equation will reduce. He said the first equation will become smaller. So that is del square V equals to minus rho by epsilon naught. And he said that, okay, second equation is not gonna be that smaller, but at least it will become a bit smaller because this term will vanish. Agreed? So this is called as Coulomb's gauge. So Coulomb said, hey, why don't we use this gauge? But Lorentz was not satisfied. Lorentz said that no, let us not use this. The second equation is still very difficult to solve. So Lorentz suggested another technique. Lorentz suggested that let us take such a vector. So this is 2. So here we discuss Lorentz gauge. Okay. So Lorentz suggested that no, let us not take del dot A equals to 0. He suggested that let us take such a magnetic vector potential such that del dot A is related to the scalar potential as minus mu naught epsilon naught dV by dt. So this was Lorentz idea. Lorentz said that hey, let us take such a potential, such a magnetic potential whose divergence is related to the scalar potential as this. Now Lorentz ingenious idea of using this type of potential made equation 1 and equation 2 much simpler. Okay. So let us see what equation 2 becomes. Now equation 2 becomes, so Lorentz said that this is equal to minus of this, so I think this part vanishes. So when this part vanishes, I am left with only del square A minus mu naught epsilon naught del square A by del t square. So don't you think this is looking somewhat like a wave equation? Okay, somewhat like a wave equation. And here we have minus mu naught j. Then when you use the Lorentz gauge in the first equation, so the first equation will look like is this. Now Lorentz was very happy. Happy because this equation 1, this big equation 1 and this another big equation 1 and this equation 2 has become nothing but two simple wave equation. So they take the exact form of wave equation when any sources is 0, and when sources are not 0 they take the form of this equation. Now these equations are much simpler than the equations 1 and 2, and even Coulomb's suggestion was not that good because the second equation in Coulomb's gauge also looks very difficult to solve. But Lorentz gauge was so beautiful that it made equation 1 and equation 2 very much simple. So what Lorentz is saying? So what is the entire conclusion? The entire conclusion is that these two equations, they contain all the information that is there inside the Maxwell equation, and this two equation has only four variables to solve, four unknowns to solve. So we have two equations and four unknowns. And Lorentz suggested, okay, solve this equation, get the answer of A and V, that will give you the general value of potential in Maxwell equation, and then you can use this potential to calculate the electric field and the general electric field and the general magnetic field. So we'll continue this lecture in the next time, and we'll see some more application of electrodynamics.